Fuzzing is a vulnerability discovery mechanism that provides random input on a tested application with the aim to crash the application. Application crashes are caused by bugs which subsequently can be utilized by attackers for the exploitation of the application. The fuzzing flow begins by selecting the target program and instrumenting it. Next, the fuzzing process begins by choosing an initial input and mutating it. The program is then executed with the mutated input, and if the code coverage is increased, the new input is added to the fuzzing queue. This cycle repeats during the fuzzing process. There are two primary approaches to fuzzing. The first approach is mutation-based fuzzing, which involves randomly mutating the input, using techniques such as bit flips or arithmetic operations. And grammar-based fuzzing, which employs more sophisticated methods that adhere to a predefined set of rules, such as dictionary-based or tree-based mutations. In a 48-hour testing program, grammar-based methods such as operators, statements, and data type changes, abstract syntax training leaf node modifications, and inline assembly node changes prove to be more effective at discovering new test cases compared to most mutation-based strategies. The only exception is bit or byte flipping, which performs on par with the grammar-based approaches. The main idea of the mutation strategy prioritization algorithm is to focus exclusively on applying the top K most effective strategies for exploring new paths. This contrasts with most fuzzers, which typically apply all strategies in a deterministic manner. When a test case is selected for the first time, every strategy is applied and evaluated based on its effectiveness, earning a score. In subsequent selections of the same test case, only the top K strategies, those with the highest scores, will be applied. This approach ensures that the most effective strategies are prioritized in future iterations. Experiments indicate that the optimal variant of the mutation strategy prioritization algorithm is achieved when K equals 5, meaning only the top 5 strategies are applied when a test case is selected for the second time. Additionally, all variants of the mutation prioritization algorithm except the one with K equals 3 outperform state-of-the-art fuzzers. In SecOPERA, we plan to evaluate mutation prioritization on the pilot use cases, for example run Zephyr OS AFL for Velopera firmware. Additionally, it can serve as a vital application layer component in order to greatly improve the performance of fuzzing. In our demonstration, we use crash program, which includes a set of branches that lead to an application crash when the given input is crash. Now we run the well-known American fuzzy lop on the crush application. AFL-GCC instruments the application for running a guided genetic algorithm. As we can see, after 1 minute no crashes were found by using the generic AFL. Now we run the AFL, but this time with a mutation prioritization strategy. Instead of applying all strategies in a deterministic manner, this time we perform only the top K strategies that are most effective in discovering new paths. As we can see, this time we discover one crash in under 1 minute.